Chapter 7, Module 1. Previously, while constructing fundamental group of a circle, we have considered one function which we have called exponential function from the real line to the unit circle S1. We have also pointed out there that this exponential map is actually an example of what we call covering projection or covering map. In this module, we are going to define what is a covering space of any arbitrary topological space, and also we define what is a covering projection. Now, we begin with the definition of covering projection, and then we will cite some examples of covering projection. We define evenly covered open set. Suppose P is a continuous surjection. An open set U of X is called evenly covered by P if P inverse U is expressed as disjoint union of open sets V alpha of X tilde such that P restricted to each V alpha is a homeomorphism of each V alpha onto U. Now, this collection V alpha of open sets in X tilde is called the partition of P inverse U into slices, and each V alpha is called a sheet over U. For each x belonging to capital X, if it has an open neighborhood U in X such that P inverse U is evenly covered by P in X tilde, then P is called a covering map, and X tilde is called a covering space of capital X. Such an open neighborhood U of X is referred to as an admissible open set. Now, for each x belonging to capital X, if we take P inverse X, then that is a subset of X tilde. This particular subset is called fiver over X, and P inverse X, as we can see from the diagram, that it is a discrete space with respect to the subspace topology of X tilde. Now, we discuss a few simple examples of covering maps and covering spaces. Let X be a topological space. The identity map Ix is a covering map, and so X is trivially a covering space of itself. This is because if I take any point x from capital X, then capital X itself is an open set containing the point x such that its inverse image under the map I is X itself, and the partition is the singleton containing the capital X space. Any homeomorphism P from X tilde to X is similarly a covering map. Now, if we take X tilde as X times 1 to n, a finite set, then that can be viewed as a covering space of X, where the covering map P is given by Pxi equal to X for each I from 1 to n. It can be seen that X tilde is a disjoint union of copies of X. If Y is a discrete space and X is any topological space, then the projection map P from X cross Y to X given by the pair xy goes to X is a covering map, and so X cross Y is a covering space of capital X. Now, this is because P inverse X can be viewed as the disjoint union of X cross singleton y, where y is varying over capital Y. Now, if I take exponential map from R to S1 given by exponential t is equal to the pair cos 2 pi t sin 2 pi t, then that is a covering map. Exponential is a continuous surjection for any point x taken from S1 minus 1 0. If we consider the open neighborhood u as S1 minus 1 0, then exponential inverse of u is disjoint union of the open intervals n to n plus 1, where n varies over the set of integers. Then of course, each n to n plus 1, that open interval, is homeomorphic to the given open set u, that is, u is evenly covered by exponential. Now, for the point 1 0, if we consider the open set V as S1 minus 1 0, then exponential inverse of V can be viewed as disjoint union of the open intervals n minus half to n plus half, where n varies over the set of integers, and each interval n minus half to n plus half is homeomorphic to V. So, V is also evenly covered by exponential. Therefore, exponential is a covering map, and thereby the real line R becomes a covering space of S1. Now, from these previous examples, we observe one thing, that covering space may not be path connected or it may be path connected. In this course, we note that we are mainly concerned with path connected spaces, and hence in what follows we shall consider only path connected, at least locally path connected spaces. Next example shows that a path connected topological space may have more than one path connected covering spaces. So, let us take this example, that S1 is a covering space of itself by the covering map P1, which is given by the expression P1z equal to z square. If I take P from S1 to S1 given by Pz equal to z to the power n for any non-zero integer n, then that P is also a covering map. So, S1 becomes a covering space with respect to the covering projection P. Now, we discuss a theorem where we see that a covering map is an open map. Let us take an open set from x tilde. Now, take any point x from P A, that is the image of A under the map P. Then there exists y in capital A such that P y equal to x. Since P is a covering map, there exists an open neighborhood u of x such that P inverse u is disjoint union of some V alphas, where V alphas are open subsets in x tilde. Now, since y is taken from A, y is in some V beta. Therefore, y is in A intersection V beta, and A intersection V beta is open in x tilde. So, A intersection V beta becomes open in V beta. Now, P restricted to V beta being a homeomorphism, P of A intersection V beta, that means the image of A intersection V beta under the map P is open in U and hence in X. So, there exists an open set P of A intersection V beta such that it is within X and P A, that means X belongs to P of A intersection V beta, which is contained in PA. The arbitrariness of X proves that PA is a neighborhood of each of its points and hence it is open in X. This theorem says that whenever P and Q are covering maps, then if we define a map from X tilde cross Y tilde to X cross Y given by P cross Q taking the pair XY to the pair Px comma Qy, then that new map P cross Q becomes a covering map and thereby X tilde cross Y tilde becomes a covering space of the product X cross Y. Now let us take a point BC from X cross Y. Then B belongs to X and C belongs to Y. By definition of covering maps, there are open neighborhoods U and V of B and C respectively in the respective spaces, such that P inverse U is disjoint union of S alphas and Q inverse V is disjoint union of some T alphas, where X alphas are open in X tilde and T alphas are open in Y tilde. Then U cross V, the Cartesian product U cross V is an open neighborhood of the pair BC in the product space X cross Y. Now the inverse image of this Cartesian product U cross V under the map P cross Q is the disjoint union of S alpha cross T beta, where each S alpha cross T beta is homeomorphic to U cross V via the restriction of P cross Q. This theorem can be applied to obtain the covering space of torus. We know that a torus is nothing but the Cartesian product of the unit circle S1 with itself, and we have already seen that the exponential map from R to S1 is a covering map. So this theorem says that exponential cross exponential is a map from R2 to S1 cross S1 is again a covering map. That means R2 becomes a covering space of the torus S1 cross S1. Now we see that restriction of a covering map need not be a covering map. This follows from the example that if we take the exponential map exp from R to S1 as usual, and we restrict that exponential map on the positive real numbers, then that particular restricted map, that is exponential restriction on R plus, is a continuous surjection, but it is not a covering map because the point 1 0 has no evenly covered open neighborhood by the restriction map. The next result gives one situation when restriction of a covering map becomes a covering map. Suppose P is a covering map from X tilde to X, and suppose Y is a subspace of capital X. If Y tilde is the set P inverse Y, then the map P restricted to Y tilde from Y tilde to Y becomes a covering map. Let us take a point B from capital Y. Since B is taken from capital X and P is a covering map, there exists an open neighborhood U of B in capital X such that U is the disjoint union of V alphas, where each V alpha is open in X tilde. Now U intersection Y is an open neighborhood of B in Y such that inverse image of u intersection y under the map P restricted to y tilde is the disjoint union of V alpha intersection y tilde. Hence, the open neighborhood u intersection y of B is evenly covered by P restricted to y tilde. Now, we recall one definition, the definition of local homeomorphism. It says that if each point x is taken from capital X has an open neighborhood u such that Fu is open in Y and the map F restricted to U is a homeomorphism, then the function f from x to y is called a local homeomorphism. We show next that a covering map P is always a local homeomorphism. Let us take a point x tilde from capital X tilde. Since P is a covering map, Px tilde has an open neighborhood U evenly covered by P. Suppose we take the collection V alpha, which forms the partition of P inverse U in x tilde, and let x tilde, small x tilde, is a point in V beta. Then V beta is the desired open neighborhood of x tilde, which is homeomorphic to U by the restriction of P on V beta. But the converse of this result need not hold. So far, we have established certain facts about the behavior of covering projections. For example, we have seen that a covering projection is an open map. We have seen that a covering projection is a local homeomorphism, but the restriction of covering projections need not be a covering projection. Now, we shall establish a very useful result regarding the quotient maps of orbit spaces. So, before proving the main result, we define or we recapitulate certain facts. We start with defining an action of a group G on a topological space X. Now, suppose G is a topological group, it acts on a topological space X, means that there is a continuous map from G cross X to X such that it has two properties as shown here. Now, any action defines an equivalence relation on the set capital X, that is given by A is related to B if and only if A is equal to G dot B, where dot stands for the action of the group G onto the topological space X. If we represent each equivalence class by x bar, then x bar consists of the points G dot x, where G is varying over capital G. Then this equivalence class is called orbit of x. Now, we collect all these equivalence classes or the orbits in the collection x by G, and we topologize x by G by the quotient topology induced by the map pi, which takes any point x to the point x bar belonging to x by G. This quotient space is called orbit space of capital X under the action of the group G. Now, we come to the main result, that suppose a group G acts on a space X such that for each x there exists an open neighborhood Vx of the point x such that Vx intersection G Vx equal to phi for all G not equal to the identity element of the group. Then the quotient map Q from X to X by G is a covering map. So, to prove this result, we start with a point x bar from X by G, then U x bar is equal to Q of Vx, where Vx is an open neighborhood of X satisfying the hypothesis of the theorem. Then Q inverse of U x bar is the disjoint union G dot Vx, where G varies over capital G. Now, Vx is open implies G dot Vx is open for all G belonging to capital G, which implies Q inverse of U x bar is open and thereby U x bar is open. Now, Q restricted to Vx is a bijection, and so by the definition of quotient map, Q restricted to Vx is a homeomorphism. Again, commutativity of the following diagram shows that Q restricted to G dot Vx is a homeomorphism for all G belonging to capital G. Therefore, Q is a covering map. Now, we go through some examples which follow immediately from the previous theorem. The quotient map Q from R to R by Z, where Z action on R is given by n dot x equal to n plus x, is a covering map. Note that the quotient space R by Z is actually S1. So, the quotient map from R to S1 expressed as n dot x equal to n plus x becomes a covering map. Similarly, if we consider the quotient map Q from R cross R to the orbit space R cross R by Z cross Z, where the action on R cross R is given by n comma m dot x comma y equal to n plus x comma m plus y, this becomes a covering map. Now, we can see that the orbit space R cross R by Z cross Z is actually the torus S1 cross S1. So, this example shows that R cross R is actually a covering space of S1 cross S1. Now, the next example shows that the quotient map Q from Sn to Rpn, the real projective space, is a covering projection. Now, Rpn is the orbit space of the action of Z2 on Sn, where Z2 means the cyclic group consisting of two elements 0 and 1, and the action is given by 1 dot x is minus x and 0 dot x is x for all x belonging to Sn. Then choosing the open ball Bx epsilon with epsilon less than half and taking the intersection of Bx epsilon with Sn, we get an open neighborhood of x such that Ux intersection 1 dot Ux is empty. So, that satisfies the hypothesis of the theorem, and thereby Q becomes a covering map. Similarly, we have another example that if we take the quotient map from minus 1 1 open interval cross S1 to minus 1 1 open interval cross S1 by Z2 under the action of Z2 on that set by 1 dot Sz equal to minus S minus Z and 0 dot Sz equal to Sz, then that also satisfies the condition of the previous theorem, and hence it is a covering projection. Now, we may observe that the orbit space minus 1 1 cross S1 by Z2 is actually a Mobius band. So, minus 1 1 cross S1 becomes a covering space of the Mobius band. We end this module with a note that covering spaces are very important in its own right and has a lot of applications in various branches of mathematics. But we shall only discuss those properties which are related to the computation of fundamental groups.